Assalamu alaikum. The topic for today's lecture is blackbody radiation. Blackbody radiation is a very famous topic in physics and it played a very pioneering role in the development of quantum mechanics. The blackbody actually is an object that absorbs all radiation incident on it irrespective of wavelength and angle of incident. In reality, there is no perfect black body. However, there is an idealization of the black body in the form of an evacuated enclosure. We also call it the cavity, having a small opening so that a light that enters in this cavity through the small hole that is reflected back and forth inside the wall of the cavity, and no portion of this light is coming out of the hole of this enclosure. So this setup behave like 100% or perfect black body. The radiant energy in the enclosure is actually a mixture of electromagnetic waves of all frequencies from 0 to infinity. So if you plot the radiant energy, or we also call it the spectral density, this is the energy per unit volume of the black body, against the frequency, so we see this type of plot where the dotted line represent the experimental plot, while the blue line represent the Planck law, the pink dashed line represent the Wien's law, and the black dotted line represent the Rayleigh's law. You see that it is only the Planck law which completely coincide with the experimental data, both at the level of low frequency as well as high frequency. However, if you look into the Wien's law, so the Wien's law perfectly explains the black body radiation at the higher frequency. However, there is a departure of the Wien's law from the experimental data at lower frequency. Similarly, if you look into the Rayleigh's law, so the Rayleigh's law explains the black body radiation at the lower frequency, but as we go to the higher frequency, so there we see a departure from the experimental data. It means that neither the Wien's law nor the Rayleigh's law completely explain the black body radiation. Keep in mind that the Wien's law and the Rayleigh's law both were based on the classical physics. However, Planck first time introduced the concept of photon, and this was the foundation stone of quantum mechanics. So Planck explained the black body radiation by introducing the concept of photon, and the radiation inside the enclosure could be regarded as a photon gas, that is an assembly of boson. So if we have an assembly of boson, so we use the Bose-Einstein statistic. So if we have a number of photons having frequency between nu and nu plus delta nu, so we can calculate this by the Bose-Einstein distribution function. So you see here, this is the Bose-Einstein distribution function formula we derived earlier. However, the shape is a little bit different. If you remember, so we derived the Bose-Einstein distribution function in the form of this equation. So here we take the chemical potential mu is equal to 0, because for black body radiation the Gibbs free energy is equal to 0, and the Gibbs free energy G is equal to mu n. So the n, which is the number of photons, that is not equal to 0, so of course the chemical potential is equal to 0, and all this explanation is given on the page number 228 in the book of Salinger. So if you put mu is equal to 0, and instead of nj we put delta n nu, which is the number of photons having frequency between nu and nu plus delta nu. However, here Nj is the number of particles in the jth level of the system, and instead of Gj we write delta G nu, which is the degeneracy, that is the number of energy states between nu and nu plus delta nu. So an assembly of photon having frequency up to nu is given by this relation, and you may remember this relation we have derived while we were discussing the device theory of specific heat. There we are represented by n, however symbolic representation is not a big deal, so here we represented by G. Now you know that an electromagnetic wave consists of two mutual perpendicular oscillations, one associated with the electric field and the other associated with the magnetic field. It means that a photon can be regarded as a sum of two linear oscillators. So what we can do, we multiply this equation 2 by 2. So the number of linear oscillators having frequencies up to nu is given by this relation. This is just 2 because of one photon could be considered as two linear oscillators. After the simplification, we have this equation. Now this equation number 3 also represents the number of possible energy states, because each frequency is associated with an energy. So the number of frequencies mean the number of oscillator or the number of energy states. So equation number 3 actually represents the number of possible energy states having frequencies up to nu. Now the degeneracy of the energy having frequency between nu and nu plus delta nu is given by this relation. This was the relation on the back slide. So delta G, so you just take delta V nu, so you have 3 nu square delta nu, and the rest of the things are exactly the same. So what you need to do, you put this delta G nu here and this equation on the previous page, and you just rearrange it, so you will have this equation. Now you divide this number by V, so what you have is the number of photons per unit volume in the frequency range nu and nu plus delta nu. Now this is the number of photons per unit volume, and we know that each photon has an energy of h nu. So if we multiply this side by h nu, so we will get the energy per unit volume. So the energy per unit volume, or we also call it the spectral energy density, and this range is given by this. So we just this h nu and h nu, so this we represent by delta nu V, delta U V, which is the spectral density or the energy per unit volume, and these are the number of photon in the energy range nu plus delta nu, and if you multiply by the photon energy, so this will give you the energy of the photon per unit volume having a frequency between nu and nu plus delta nu. Okay, so if we rearrange the equation on the back slide by keeping the constant on one side and the variable on the other side, so we have this equation number 7, which is known as the Planck law of blackbody radiation. If we compare the Planck law with the experimental data, which is given by this black dot, red dot, and the Planck law is given by this yellow line, so you see that the Planck law completely explain the experimental data for the blackbody radiation, both in the lower wavelength range and the higher wavelength range. Now we have two cases of low frequency and higher frequency. So if we consider the higher frequency case, so you will have h nu by kT quite larger than 1, and in that case this value also go very higher, and subtraction of just 1 has no big effect, so you can write this as e to the power h nu by kT. Now if you put this in equation number 7, so you have this relation given by equation number 8, and this is the Wien's law of blackbody radiation. So you see here that the Planck law reduce the blackbody radiation to Wien's law at the limit of higher frequencies. Now, if we consider the case of low frequency, so you will see that h nu by kt could be less than 1, and if you expand this and ignore the square and higher power of h nu by kt, because nu is lower value, so you will have this thing. Now if you put this value in equation number 7, so you will have this relation given by equation number 9, and this is known as the Rayleigh's law. So you see here the beauty of Planck law, that it reduces to the Wien's law at the limit of higher frequency, and it reduces to the Rayleigh's law at the limit of low frequency, and it also correctly explains the experimental data. So that is why the Planck law is very successful by considering the photon concept, and this was the very pioneering step in the development of the quantum mechanics. And you know that in quantum mechanics, whenever we have a departure from the classical law, so that quantum mechanical laws reduces to the classical laws under certain limitation. Now, if we want to know about the total energy from 0 to infinity, so we have to integrate equation in the Planck law. So we are here. Now we have to solve this integral, and for this we do a supposition that let h nu by kt is equal to x, and that case nu is equal to kt by h into x, and dv is equal to kt by h into dx. So if we make this supposition and this integral, so we get this one. After rearrangement, so we have this one. Now you remember this equation when we were talking about the specific heat in the device theory. So this is equal to pi 4 divided by 15. So if we rearrange this equation, so we are here at equation number 10, which is known as the Stefan-Boltzmann law, and this sigma, which is equal to this one, is known as the Stefan-Boltzmann constant. So this was all about the blackbody radiation. Next topic will be about the paramagnetism. Okay, thank you. Allah Hafiz.